Continuing with ice tables, we now want to look at some problems or some situations where we need to maybe use a little heavier lifting when it comes to our mathematical tools. What are the equilibrium concentrations if the initial concentration of C2H4 is equal to 1.0 molar? My reaction is 2C2H4 becomes C4H8, and Kc is equal to 2.2.
All right, I want to know the equilibrium concentrations if the initial concentration of C2H4 is 1. And you'll note this format right here with little 0 there, that's a throwback to our kinetics, where you put the subscript after the bracket to say what time it is. So that's at time 0, the initial concentration. So if I want equilibrium concentrations, it's going to be all about my ice table. So I got 2 C2H4 gas in equilibrium with C4H8 gas, ICE. So my initial concentration of C2H4 is 1 molar. Because there's no information given about C4H8, that's a 0. Because that initial concentration is 0, the shift has to be to the product side of the reaction. So we have to put a plus there. 2, or the reactant side is, if we're shifting to the product, the reactant side, that concentration has to be decreasing. So I know my signs have to be opposite on the two sides of the reaction. In terms of the amount of how much, I can say minus 2x, and this is going to be plus x, where the 1 coefficient is a 1 coefficient, 2 coefficient is a 2 coefficient. E, I put those together, 1 minus 2x, and 0 plus x is x. So that gives me a nice representation of those. And so I can take these, and I know that for my Kc is going to be equal to the concentration of C4H8 divided by the concentration of C2H4 squared. Okay, so then I take these, and basically the 1 minus 2x, that's going to go in right there, and the x is going to go in right there. So I can plug that in, and I can plug in the value for Kc, it's 2.2. So I get my equation that I'm looking at overall is I get 2.2 is equal to x divided by 1 minus 2x squared. And what I want to do is solve for x. And so the ice table is done here. Right? My ice table use, my setup, I got that working well. And so now what we want to do is actually solve for x. And so this is going to be, we're going to get a little bit of algebra practice in. So first off, 1 minus 2x squared. We know that that is really 1 minus 2x times 1 minus 2x. We can FOIL that. Right? First, outsides, insides last. So 1 times 1 is 1, minus 2x, minus 2x, plus 4x squared. So I get 1 minus 4x plus 4x squared. So that goes down here. So I have 2.2 is equal to x divided by 1 minus 4x plus 4x squared. Take that numerator, or that denominator, multiply it over here to get it out of the denominator. And I get 2.2 times 1 minus 4x plus, whoops, there shouldn't be that, plus 4x squared is equal to x. 2 distributed in. 2.2 minus 8.8x plus 8.8x squared is equal to x. Can subtract out the x from both sides, and I end up getting 2.2 minus 9.8x plus 8.8x squared equals 0. So I have a polynomial here, that I need to be solving for. I'm trying to solve for the x, and it's a quadratic. And so in order to solve this, I can rearrange it. Get 8.8x squared minus 9.8x plus 2.2. I need to factor it. So with rearranging, I've just written them in a different order. And what I can see from that is that this 8.8 I could call A, the negative 9.8 I could call B, and the 2.2 I could call C. If I define those in such that way, I can use my good friend, the quadratic equation, in order to solve for those roots. Negative B plus or minus the square root of B squared minus 4AC all over 2A. You took algebra. Maybe I asked teacher, when are you ever going to need to use this quadratic equation? Well, I could have just told you chemistry class. Quadratic equation is back. We can use it to solve as an algebraic tool to solve for x. So A goes everywhere we see A, that's the term on the x squared. B goes everywhere we see B, that's the term on the x. And the C is the ones term, no x's. You do have to have a 0 on the other side. You will note there's the plus or minus, so there are two solutions to this. So when we plug it in, I get x is equal to negative 9.8. That negative, that subtraction sign is a negative on the 9.8. Plus or minus the square root of, again, negative 9.8 squared, doesn't matter as much there. For A is 8.8, C is 2.2, all over 2 times 8.8. And so we can take those values, substitute them in for the A, B, and C. But again, we do have these two, the plus or minus. And so what that means is you have two results. You have a plus result and you have a negative result. So I won't go through that's arithmetic at that point in time. So you can do it and you put a plus sign, or you do it and you get a negative sign. And as a result, your two solutions are x is equal to 0.80 and x is equal to 0.31. So mathematically, both of those work. In terms of just, we use an ICE table to set up this algebraic equation, right? This algebraic expression. And for that algebraic expression, there are two solutions. X can either be 0.8 or it can be 0.31. There is only one chemical equilibrium. There are not two equilibrium states for a given reaction. So only one of these is the right answer. And we will need to check both of them to see which one is right. How we do that is we use these expressions that we got out of the ICE table. Remember, we have that the concentration of C2H4 is going to be 1 minus 2x, and the concentration of C4H8 is going to be x. So these values of x, both values of x solve for the Kc, but they don't give you necessarily real concentrations. What I mean by that is, let's see what the actual concentrations are. Concentration of C2H4 is 1 minus 2 times 0.80, and the concentration of C4H8 would be equal to 0.0. Okay? If we calculate that out, we get that is equal to negative 0.60 molar. That is impossible. You cannot have a negative molarity. That is impossible. That cannot happen. And so as a result, this X is a mathematical answer, but it's not a chemical answer. This is similar to the fact that we round our answers to sig figs. We, use units on our answers. This isn't a math class. We use math as a tool, but our numbers really mean something in real life. These are physical values that we need to respect. So this is not the right answer. Instead, when x equals 0.31, we can see that the concentration of C2H4 is equal to 1 minus 2 times 0.31, right? We plug in the different value of x. That gives us an answer of 0.38 molar. And the concentration of C4H8 is just x, or 0.31 molar. And so these are the real answers. Those are both possible values. Negative molarity is impossible. You can't have a negative number of moles. It is possible to have zeros, okay, or 0.31, 0.38. Those are totally reasonable to have positive numbers. These are physical concentrations. This is a mathematical answer. It's not a physical answer. It doesn't describe real life because you don't have a negative concentration. Yes, it would be equilibrium if the concentration was negative, but that's impossible. So that never happens. This is what the equilibrium concentrations are. Again, we can also at the end check if we want. We know that Kc is going to be the concentration of C4H8 divided by the concentration of C2H4 squared. And so we can plug in the numbers we got. So 0.31 divided by 0.38 squared. And that gives us 2.1. Our answer, or our value that we started with was 2.2. I'm going to call that good. I'm going to call that close enough. So those are the equilibrium concentrations. You know, getting through with the quadratic equation takes some time, but we can still get the answers that we are interested in.
While this may be a difficult process or a long and tedious process to come up with these equilibrium concentrations, they are relevant and important. C2H4 is ethylene. This is a really, really common feedstock in petrochemical industry. And so say you want to do reactions with C2H4, if you want to store C2H4, you have it, say, in a giant container, this is the chemistry that it's going to start doing. It is going to undergo a reaction and become some C4H8. This is just a process that happens. These are going to be in equilibrium. And so this is something you need to be mindful of if you're going to be storing C2H4 and you want it to stay as C2H4. So functionally what they do is when you store them, you see these giant tanks of it. What they're doing is they store it at very cold temperatures. I mean, very, very cold temperatures. What that does is slow down the kinetics. So you put in the C2H4 and then it just never reaches equilibrium. It just never reaches equilibrium because it's so cold, so it just stays C2H4. The collisions will never have a high enough energy. And so that's what you're using, the idea of just basically making it so cold that it becomes kinetically, the reaction takes years to reach equilibrium. And that's generally the strategy, because this would be a big problem. And this is a common problem whenever you're working with C2H4, that it will react and become C4H8.
Participation 218. Got one more video. See if we find any more questions there. See you in the last one.